All right, so today we're going to take a look at section 5.4, which is exponential functions. We're going to look at differentiation and integration. So part of what you're seeing happen on this today is stuff that will be on the derivatives basic skills quiz next week, and part of it isn't. But all of it is taught in the same section in your textbook. So first of all, we're going to take a look at the natural exponential function. So you've seen the function y equals ln x, right? We've worked with that now in a couple class periods. And this is called the natural exponential function. The inverse of it is. And its equation you've seen before as well. It's, well, I'll use the inverse notation first, f inverse of x, and the notation is e to the x. That is y equals e to the x if and only if x equals the natural log of y. And we worked on inverse functions last class. That was 5.3, right? We talked about switching y and x, solving for y, and all of that stuff. Well, the problem if you take a look at this particular function and this idea is that if you take this function, y equal ln x, and you try to switch the x and the y, so you write down x equals ln y, kind of like I have here at the end, right? The question is, well, how do I get y alone? What do I do to get it solved for y? Because now the y is inside of a log. So it's kind of like, what happens when the y is in the denominator? I've had a couple of students in my office this morning asking me I had a y in the denominator. What do I do to get that out? Well, when you have a denominator y, you multiply by it. Well, this is a logarithmic function, and the inverse of a logarithmic function is an exponential function. There's a lot of ways to see that. One of them is to simply remember that it rewrites itself as y equals e to the x. There's a couple of other ways that you may have seen, so I want to draw your attention to in case this is something you've seen before. If you haven't, it's fine to know about it. One is that you may have seen logs before you ever saw natural logs. And somebody introduced this idea of the ln to you as the log with a base of e. Maybe you've seen that, maybe you haven't. It's not a big deal either way. But the helpful thing to think about this is that I always learned to rewrite like this. So you start by rewriting with whatever your base is. So my base is e. And you cross to the other side of, this isn't written the way I want it to be written. Let me try one more time. Here we go. Go to the other side before you land by itself. There we go. So you start with the base of e, and you cross to the other side of the equation, and that other side of the equation is your new exponent, x. And then it equals where you quote-unquote land, where the arrow lands, and that's equal to y. So I always learned to rewrite exponentials like this. My logarithms turn into exponentials by doing these sort of circles. And I had a teacher I was observing once. I was doing like a student-teacher kind of thing. And I was observing this student teaching, and they called it a scorpion tail. And I thought that was very apropos. It was in Kansas that it happened. But it was shortly after that fact that I actually saw my first scorpion in real life, and so it really stuck with me. So this idea of swinging this arrow around, this tail around, to be able to rewrite it. Now, in order to kind of be able to work with these, we have to understand some properties of exponents. And there are 6 different exponential properties that I want to remind you of. And these are the initial, first half of the 6. And what we want to do is be able to rewrite them so that they are expressed in a way that's usually more easy to handle. For instance, on the first one, we have a to the m times a to the n. What's another way that I could write that might be more helpful? Yeah, this property is actually taking 2 bases that are the same, a, they could be the same or different exponents, and you can actually combine them with exponents like this. And the reason that works, and you guys have seen this before, is for instance, if you had a squared times a cubed, well, a squared is a times a, and a cubed is a times a times a, and how many a's did I have? 5 of them. Well, how do you get from 2 and 3 to 5? You add. You add the exponents, right? So that's why that's working here. And the same thing happens on number 2, except that it's division, so instead of adding, you subtract. And I could do the same sort of a manipulation here with the numbers that I did. So if I had a to the fourth over a to the first, I could write out that this is 4a's, 1, 2, 3, 4 over 1a. I could then reduce one of my a's, right? And that leaves me with a to the third. And again, how do I get from 4 and 1 to 3? I subtract. Okay, so it's not division, it's actually subtraction. How is 3 different from 1 and how it looks to begin with?
The exponent is multiplying by the other exponent.
That's what the end result's going to look like. What does it look like that makes you know it's different than number 1?
There's not two A's.
There's not 2 a's. Okay? On number 1, I have a to the m, and I also have an a to the n. On number 3, I only have the exponent's base, that a, written down one time. Okay? So on that one, I have an exponent raised to an exponent. It's going to do exactly what Chelsea, I think, was the one who said it, where I will write them as the 2 exponents multiplied, m times n. And again, we could look at that from the perspective over here of an example where I would say, okay, well, let's do a squared cubed. Well, a squared means a times a, and cubing it means I would have a times a 3 times. How many a's do I have? I've got 6 of them. How do I get from 2 and 3 to 6? I multiply. So there's a multiplication factor there instead of an addition factor like on number 1. Okay, so 4 and 5 are awfully similar, right? I've got something inside going on, and it's raised to one exponent on the outside. In this case, it's an m. Now, this is a really helpful feature. What happens when I have ab to the m? Right. So I can write that as a to the m, b to the m. And we can do a little one over here. We're just going to do ab squared. That should be ab times ab. But one of the things you learned about multiplication is that multiplication is what we call commutative, which means I can change the order around, right? So I can manipulate the fact that this is a, b, and I could put it a, and then b, and it would be the same thing. That's a property of multiplication. I'm allowed to rewrite the order of things from multiplying. And then, of course, that's a squared, b squared, right? Because I've got 2 a's and 2 b's. And now my screen's frozen. I'm sorry about that. 5 will do, and then I'm going to make a comment about 4 and 5. 5 has a over b to the m. So what do we do? Yeah, it's the same thing, right? A to the m over b to the m. And I'm not going to show an example because it's going to look exactly like the last example. In fact, cleaner even. But what I want to make mention of right here is what you don't see happen. What you don't see happen is any property that looks like this. There's nothing on there that looks like that, is there? And you might sort of think to yourself, why? And we're going to do a concrete example right here real quick of why a plus b to the m does not distribute that way. Let's just say that we had a plus b squared. Well, if you were working with algebra, somebody along the way should have said that this is a plus b times a plus b. Right? Now what happens if you try and multiply those two quantities together? What do you get? You get 3 terms. Do you know what they are, Taylor?
A squared plus a
2 ab's when you combine them. And then b squared. Notice it's not just a squared plus b squared, right? That would actually somehow be missing that middle 2ab term. And the same thing happens if we deal with square roots. And I mention it only because it came up on your last homework, and somebody was working with me in the office about this, asking a slightly different question, but I made mention that if you have a square root, you're not allowed to simply apply a square root to each term. And the reason that you're not, this is not equal, is for the exact same reason that this doesn't work. That would be distributing an exponent, is what it would be doing. Because a 1/2 exponent is the equivalent of a square root, right? So you can't just distribute exponents across addition or subtraction. Multiplication, division, absolutely. Addition, subtraction, we can't do that. All right, it simply will not work with the numbers that we're working with. All right, the last one, number 6. What is different about 6 than 5?
Negative exponent.
The negative exponent. Do you remember what negative exponents do? Yeah, they flip fractions upside down. Or if you simply had a negative exponent, like in the numerator, you would move whatever that quantity is down to the denominator, or vice versa, right? We don't leave answers with negative exponents in their quantity or in their final form. So this one can actually be flipped, so it becomes b over a. And then I can distribute the m just like I did on number 5. So this is b to the m over a to the m. Okay, now, you guys know most of that. I know you do. I mean, you've been working with that a lot. But I want to remind you, because we're going to see some of that happening within some of the problems. And if you identify something like that happening, it's going to be a lot easier. It's kind of like on the homework that I just gave back to you. Some of you did problems and you got right solutions, but you didn't use log properties, and so you did a lot more work than you had to. In fact, on most of them I wrote a note to you and I said, if you'd used log properties, it's been a lot easier. Or because you didn't use log properties, you made errors that you wouldn't have even had a chance to make. Same thing here. Exponential properties can be very helpful as you're working through these. So let's take a look at some algebra issues to start with. We're simply going to be solving. The goal is to solve for x. And then it says accurate to 3 decimals on this one. So we're going to use our calculator at the end to find out what the solution would be with the 3 decimal answer, okay? So our goal is to simply get x equals at the end. So what am I going to do first? Plus 6 sounds like a good spot to start. All right. So now I have 3e to the x equals what? 14. Fabulous. Now what? Wonderful. Divide by 3. I'm going to leave it for the moment this written as 14/3 since it doesn't simplify anyway. I know that I need to get a solution at the end accurate to 3 decimals. I don't want to round too soon, so I'm just going to leave it as 14/3 for now. All right, now how am I going to write e to the x equals 14 over 3 so that it says x equals? Natural log on both sides, exactly, that's right. So if I put the natural log on both sides, then the natural log, well, what actually is really going to happen is this exponent of x is going to come down. And then what is the natural log of e? That's 1, and we recounted that property before, right? This part right here equals 1. So right now I've got, in fact, let me rewrite it this way. I've got x on the left, and I've got the natural log of 14 over 3 on the right. So that's the exact solution. I want to see the exact solution written somewhere on your paper, okay? Then you're going to change that into a decimal approximation because it asks you to do that as well. It's not an exact value, right? It's an approximation. So if you take your calculator and you plug in natural log, parenthesis, which it should automatically do the parenthesis on most of your calculators, 14 over 3 in parenthesis, what does it give you correct to 3 decimal places? 1 point what? 540. And Taylor, do we need to include the 0? Yes, we do. Why? Because it asks me for 3 decimal places. That's exactly right. So yeah, it's important in this particular situation to include it. Yeah. Any questions on that one? Okay, that's an algebra question, something from college algebra that you've probably seen before. So is the next one, so let's try it from the other perspective. This one says the natural log of 4x equals 1. All right, so this is one of those ones where the way that I would change it looks like I would do that thing called the scorpion tail that I said. So that's how I'm going to show you to do it. You can do it different ways. It doesn't bother me whatsoever. But the way that I think about doing it is writing this as log base e of 4x equals 1. I start with the base and I draw my line around so that I land right next to it. E is the new base. What's the exponent? Is it the 4x as the exponent, or is it the 1 as my exponent? It's the 1. It's the part that's on the other side, hence following the arrow around. I cross paths with 1 before I land on the 4x. And then I would end up with equals 4x. You can leave that written as e to the 1 if you really want to. How else could you just write it? E, because it's just a power of 1. So this is really just e equals 4x. How do I solve for x? Divide by 4. So x actually in this problem equals e over 4. But the directions again say that I'm supposed to get an approximation for 3 decimal places. So to 3 decimal places, what is e over 4? And your calculator, depending on how your e button does it, may force you to put in an exponent of 1. We got another 0 going on there, don't we, Taylor? Yeah, 680. Okay. All right, just like we did in the last sections, or the first 2 sections actually, talking about graphs, we're going to take a look next at the graph, the general shape of this graph. So the general shape of this graph is actually the green one here on top. Okay? So let me change this to green so that I can use the color I just said it was. Okay, it's just not going to work. Try again. All right, this green on top is the graph of e to the x. All right, so a few features of it. It has a y-intercept. Its y-intercept is at 0, 1. Okay, so right here it's crossing at 0, 1. That's a 0. It doesn't look like it because my pen dragged, but it's a 0. There is no x-intercept. It actually levels off at that x-axis. So I don't have an x-intercept. It doesn't cross. It has a horizontal asymptote at y equals 0. That's the x-axis. So that's why you're not seeing it cross this axis, is because down here, this is treating this as an asymptote, okay, for the green graph. It's increasing without bound. Okay, so a reminder of what that means is increasing. It means from left to right, the graph is going uphill. And without bound means that it will keep doing it forever. And it will go higher and higher. It doesn't have any sort of cap or leveling off, features to it. That idea of increasing without bound is a limiting idea, and you've seen it happen before. Let me remind you, if you were to talk about this and talk about the limit as x goes to infinity of this graph e to the x, then it would be infinity. All right, so looking at this graph, the green one, what is the domain? Yeah, the domain is all reals. So either that all reals notation or the negative infinity to infinity notation would be fine. What's the range on this green graph? Yeah, this one is 0 to infinity. We talked last time as well that if you really so desired, I think we did this in this class, you could put that as r plus. It's only the positive values and positive real numbers. The interval notation is a little bit more helpful to us as we move forward, but you could use either one. A couple of other features here is that it's continuous and 1 to 1. So continuous means you can draw it without lifting your pencil. 1 to 1. Okay, so we talked about that last time. So somebody tell me, what does 1 to 1 mean? Exactly, only one x. So, and we had a line test to do it too, didn't we? A horizontal. So if we were to draw a horizontal line and cross through a y value, it would correspond to exactly one x value. Very good. And then this is concave up, agreed? All right, so you might be looking at this and saying, all right, great, well then why in the world is there another picture on this sheet? And the reason that there is another picture on here is because I want you to recognize something that's going on. Do you know what that other graph was?
Inverse.
That was y equal ln x. It is the inverse graph. My line's not very straight, but it's almost there. So if I drew in the line y equal x and I folded these along that line y equal x, I'd have the same graph. This is the inverse graph, the natural log x that we've already encountered and worked with. Okay. Okay, now thinking about this graph, we are going to work a little bit just like you did in the last section, or section 1 when you were introduced to log graphs. With graphs, they're going to ask you 2 or 3 questions where you actually have to shift some graphs around, so I want to remind you of how that works. Is everyone okay with this slide for me to move to the next one? Okay. So some transformations. So there's 4 types of transformations that can happen, and we've sort of talked about these before, but I didn't concretely write them this way before. So the first feature that you see happening is the ones where there's addition. You see the plus C and you see the plus D, okay? Anytime you have addition or subtraction, all that does is it takes the graph and it moves it either left and right or up and down, okay? So we're actually going to do these out of order since I've already spoken out of order, and we're going to jump down here to C. C actually moves this left or right. So if C is greater than 0, it's actually going to shift this left. So if the C is a 5, it's going to move the entire graph left 5. That graph that I drew in green before, we take it up, pick it up, move it left 5. Okay? Now if the C is negative, it's going to shift it right. Remember, anything that happens that shifts left or right, or however reflections go, they do opposite of what we'd expect. So this one's a shift right. In this case, absolute value C, because it's actually C units, but C was a negative number. So if C were negative 5, we would move it right 5. Not right negative 5, because that doesn't make any sense. Okay, so we're still going to be shifting it a positive units, in this case to the right. D happens like it should. I say should, like we expect it to anyway, right? So D is a shift up and down. So if D is positive, how do we shift? Up. So this is a shift up, D. And if D is negative, it will do what? It will shift it down, and again, just for technicality, I mean absolute D, value of D, like the actual quantity, not the sign value. Okay, so whatever the quantity was. Okay, so if D is negative 5, it will shift it down 5. Okay, A and B are actually things that stretch it out of shape. Okay, so imagine like a slinky, right? So you stretch the slinky out and you squish the slinky in, okay? Or imagine an ice cream sandwich. You can pull, or Oreos, right? You pull it apart and you squish it in, okay? So when you squish it in, it also sort of looks like it squishes out, doesn't it? Right? You know, when you do an ice cream sandwich, you squish that ice cream sandwich down, or a mud pie or whatever, it oozes out the sides. So they have sort of a relationship to one another, but technically the way it works is this. If you have, we'll do it in order. A is actually affecting the outer edges of the graph. This is a vertical stretch. Let me do A is greater than 0, or greater than 1 first. If A is greater than 1, then this is a vertical stretch. So imagine taking the ends of your graph, and a parabola is the easiest one to kind of think about this because I can do it on the ends of the graph on both sides. So imagine you've got a parabola, okay, and you take the ends of the parabola and you stretch it up. Not only is it going to make it look taller, it's also actually going to end up making it look skinnier, doesn't it? It's actually going to look like it's squished in. It really didn't, but that's the image that you see when you're done with it, kind of like the images when you go to the funhouse mirrors, right? When it makes you look taller, it also makes you look thinner at the same time. It does both things at the same time. But this is a stretch up. So when A is greater than 1, you've got to stretch up. The other option is that A is actually between 0 and 1. Okay, so you're talking fractions like 1/2 or 1/3 or 2/3 or something like that. This is actually a vertical shrink or a vertical compression. I'm going to put shrink because I'm out of space. Okay, so again, you've got that parabola, and it's like you're squishing it in. So it's that ice cream sandwich look, right? You're going like this to it. You're squishing it in. Okay, and so not only does it look shorter, it actually ends up making it look fatter as well. Okay, it does those things at the same time. All right, B is affecting the opposite, and so instead of being vertical, it's going to affect horizontal. So we've also got a B greater than 1, and we've got the B between 0 and 1. We'll talk about negative here in just a sec, but B greater than 1. So if B is greater than 1, this is going to be a horizontal, but it happens opposite. So this is a horizontal shrink or compression, yes. Okay, so imagine now you're talking about the horizontal. That is how far something goes left and right, all right? So if you compress something horizontally, you squish it in, which also ends up usually making it look taller, right? You're really making it thinner, right? You're squishing it in, but by doing so, it often makes it look like, when you just look at the image, that it's also taller. So a horizontal shrink looks a lot like a vertical stretch, doesn't it? So when you squish it in, it looks a lot like when you pull it up, okay? And then the opposite is true for between 0 and 1 as well. So if you have b between 0 and 1, you've got a horizontal stretch. Okay, so if you stretch it horizontally like this and you pull it out, it makes it look wider, but it also makes it look somewhat shorter because of the way we've sort of look at the whole picture at the same time. All right, so funhouse, this is all about the funhouse mirrors right here. This is what you've got, okay? So Halloween coming up, that makes sense. All right, so let's actually move into some calculus part of what's going on in this section. So we're going to look at derivatives. Now, this is a new derivative. You have not seen this derivative before. You've seen something that sort of looks like it might have been related to this, but it wasn't. So this is what we've got. We've got a function that says f of x equals e to the x, or y equals e to the x if you prefer. And we want to know what in the world is its derivative. Well, e is the best one ever. His derivative is himself. It doesn't get any better than that, does it? Now, notice what's different between this and this. This one had a derivative that looked like this. Right? It's a different function. What's different about these two functions?
The exponent moves down, is subtracted.
That's different about the derivative, how we treat the derivative. But what's different about the original function itself?
There's two variables.
E is a number, and where is it located right now, Jordan? Not in the exponent. The issue is where in the world is the variable? That's the difference. You see, the variable in the function we're looking at up here is actually in the exponent, whereas the variable down here, the one you've worked with before, is in the base. And that makes all the difference in the world. So you have to figure out which function you're working with based on where in the world is my variable. If my variable's in the base, it's a power rule. If my variable's in the exponent, it's an exponential rule. Okay, it's an easy mistake to make. So identify to yourself where is my variable, and that tells you which function you're working with. All right, so we're going to do some. And I want to do this one in particular because some of you really struggled when we countered one of these in class last time and you were doing a U substitution. First issue is, what do you see here? There's a product rule here. Okay? Some of you are missing seeing a product rule. You had at some point, the problem you were looking at was x ln x. And some of you were treating that as though you could just take the derivative of each of the pieces and push them back together. But you had a product rule. So you guys remember what I'm talking about, because about half the groups did that. Okay? So this is a product rule as well. So with a product rule, we actually have to apply the product rule in the midst of applying this new rule about derivatives, right? All right. So I'm going to start with y prime, and I want you to notice this too, because a few of you are getting really sloppy on your notation. You'll write down derivatives for me, but you didn't identify you actually took a derivative. Okay? So if you're rewriting something, it should say y equals. If you have some reason to rewrite something, if you're actually taking a derivative, it should say y prime, or dy dx if you like the notation better. But it needs to be labeled properly with what you've done to it. All right, so product rule, what do you want to do first? Okay, so Janet says she wants to take the derivative of the x squared, which is 2x. Then what? Times e to the negative x. So we take the derivative of the first piece and we leave the second piece alone. Okay, so this is one order of doing it. Then what? Plus the x squared. So now we're going to leave the first piece alone. And now I need the derivative of the e to the negative x. Well, the derivative of e to the x is e to the x. So I'm going to start out with e to the negative x. But what's different here? The negative x. So I also have to take the derivative of the negative x. That's a chain rule issue. It's not a complicated one, but it is a chain rule issue. And the derivative of negative x is negative 1. Okay, so basic skills quiz, you stop right there. Okay, and you could definitely see something like this on a basic skills quiz. This is not a complicated question. It's a little weird. It's the first time you maybe have seen it. Some of you it's not, but it's not terribly complicated. But you're not going to leave this like this today, right? No, you're not. You're going to do a couple of things. One of the things you might sort of recognize that you're going to do is you're going to rewrite this with that negative put through as a subtraction. Right? Typically what you're not going to see, let me make this comment, is you're not going to see that e to the negative x worrying about the negative exponent. It started out with a negative exponent in the problem. It's okay to have a negative exponent in the answer. Okay, so I don't need to worry about moving that negative exponent to the denominator. I don't have to do that piece. But what you will see happen often if you're looking at a solution, if you choose to leave it like this, I'm okay with that. But if you're looking at the back of the book, what you're likely to see them do is you're likely to see them factor this in a helpful way. So what in the world do these two terms, here and here, have in common? They have an x and they have an e to the negative x. They have both those things, don't they? So if I take x e to the negative x out of the first term, which was 2x e to the negative x, what do I have left? 2. And with the second piece, what do I have left? X. And the subtraction sign still remains between them. There's a lot of reasons that you might want to do this. If you were going on in this problem from here to doing a second derivative, it might be helpful to factor it. There would be a definite possibility. It looks nice and clean, very condensed and concise to write it that way. But if you were to leave it like this, I would be okay with that. Okay? Either of these two at the end is an alright solution by me. Sound good? Alright, let's try another one. A little bit more complicated. What about this is more complicated?
Quotient.
It's a quotient rule. Yep, it is. And I've also got more going on in one of those exponents, don't I? Well, I mean, I've got more going on both of them. I've got 2 times x. They're not complicated, but I do have a little bit more to look at in those exponents. There's actually a simpler way to deal with this problem. I want to do it exactly as is for you to see first, and then we'll deal with something else in a minute. But oh, there's a typo on this. No wonder. I was like, that doesn't look right. Yours has it down here, doesn't it? Let me get it written correctly. There we go. That eliminates my concern of what I was about to deal with. Okay, so yours looks like that, yeah? Okay, good. All right, so we have a quotient rule. So what in the world does your quotient rule say to do? Say it again for me, Jordan. All right, so I rewrite the bottom, e to the 2x plus 1, times the derivative of the top. So what is the derivative of e to the 2x? Yeah, e to the 2x times 2, or 2e to the 2x. So I'm going to do it in this order since it mirrors what we did in the last problem. Do e to the derivative of e to a power is e to the power times whatever the derivative of the power is, which in this case is 2. What comes next? Good. Minus the top, which is e to the 2x. Now we need the derivative of the bottom. So what is the derivative of e to the 2x plus 1? E to the 2x times 2. Well, that looks familiar, doesn't it? And then I've already drawn in a line because there's a denominator going on here. What's my denominator going to look like in this problem? The bottom squared. E to the 2x plus 1 squared. Okay, if you were doing this on the basic skills quiz, you stop right there. But we're not on a basic skills quiz today, so we're going to keep going. And it might be helpful to notice on this one that you could distribute things out, that would be fine, or you could factor things out, and that'd be fine too. I'm going to distribute out this time, just because. So I'm actually going to multiply everything through right now, and the way that a couple of you were mentioning is that you can write this as 2e to the 2x. And the same thing here. So if we have that 2e to the 2x times the e to the 2x here, I've got a 2. That part's fine. What is e to the 2x times e to the 2x? Okay. You're halfway right, Janet. Part of that's correct and part's not. Okay, so you've got the same thing that Janet said, 4x squared. It is just 4x. Why? Because you're supposed to add them. This is those exponent rules that we went over, remember? This was the very first one. When you have the same base, in this case it's base e, and you have exponent 2x and exponent 2x, you should be adding the exponents, not multiplying them, right? 2x plus 2x is 4x, not 4x squared, which is what you would have gotten if you'd multiplied. All right, and then we're going to distribute the same thing to this number 1. So this is plus e to the 2x. I've got a negative over here. It comes from the quotient rule itself, that negative in the middle. And then I've got that same 2e to the 2x. Now I've got it multiplied by e to the 2x, which gives me what? Yes, but I have a coefficient of 2 still, right? All right, okay, so good. 2e to the 4x. All written over e to the 2x plus the 1 squared. Now what? How nice is that? Those actually end up adding to 0. So my total, when I'm done with the problem, is 2e to the 2x over the e to the 2x plus quantity 1 squared. Now notice this. It originally started as y equals. My first thing I did, because I didn't need to do any simplification, was I wrote down the next thing I'm going to do is y prime. It's a derivative. I didn't actually have anything in front of these two equal signs, which is okay, because I'm still doing pieces of the derivative all the way along. Every step was equal to the next one. Now, if you want to, you can of course put the y prime here. That would be great. But if you didn't, it'd be okay, because those were all the same quantity continuing along the process. Okay? You do need the equal sign, however. You can't just write the next step without anything in front of it. So if you've got steps that are all equal, you need to say that they're all equal. Okay? All right. We're going to do one more of these, except it has a little bit different directions. It wants us to find the second derivative. You guys know how to do that, because I know that you did it last semester, right? So let's start with the first derivative. When I find the first derivative, you have a couple options. You could distribute this out if you wanted to. I mean, you could distribute this through. I'm going to treat it just like it is, because it was given to me that way, just because, again, you have a choice. I'm going to treat it as a product rule. Okay? Everybody good with that? You're at least not complaining, so I'm going to go with it. Okay. So we've got a derivative here. What piece of this do you want to do first? Take the derivative of the second. So you want me to rewrite the first piece and take the derivative of the second. I'm going to rewrite the first one then. Oh, come on. 3 plus 2x, and then the derivative of the second one is what? So what's the derivative of e to the negative 3x? Oh, good job, guys. Times negative 3. In fact, I'm going to write it like this. Okay. Oops. Now, it's a product, not a quotient, so I'm going to do addition. Now what?
2 times e to the negative 3x.
Okay, so where did the 2 come from?
From 3 plus 2x.
Right. Okay, so the derivative of the first part, right? So it doesn't look too bad, right? We did the derivative. That's great. However, this is one of those reasons, this is one of those places where it becomes very helpful if you really did simplify, because you're about to take another derivative. So I'm going to suggest that we do, in fact, simplify this. We're going to pull out what they have in common. So what do they have in common? E to the negative 3x. All right, then. So on the first part, what's left? Well, I've got 3 plus 2x left. Oops, but that's times negative 3. I didn't do that, did I? So this negative 3 can be multiplied by each of these, because it's left as well. So I don't have 3, I have negative 9. And I don't have 2x, I have negative 6x. Okay, what do I have left from my second term over here? 2. So taking a look at this, I have e to the negative 3x, and then I have what? I don't know why that 2 looks all funny.
Negative 7 plus minus 6.
Yeah, negative 7 minus 6x. And the reason that's extremely helpful, well, not extremely maybe, but it's at least somewhat helpful, is because that looks a lot like where I began. I mean, the numbers are different. You know, the numbers have been changed to protect the innocent, but it's the same problem that I started with, isn't it? I've got some little polynomial with some addition or subtraction in it, and I've got an exponential, and there's a product and they're multiplied. So I can treat the problem exactly the same way as I did before. I have them written in the opposite order, but that doesn't really matter either, okay? I'm going to write down my first piece first without doing any derivatives. All right? If I do that, then I need the derivative of the second piece. So what is the derivative of negative 7 minus 6x? Right. Okay, now I need the derivative of the e to the negative 3x. Okay, so somebody say it real quick.
E to the negative 3x.
Right. And I rewrite the second piece as is, right? Okay, so I can factor out just like I did on the first time around. I can write this as e to the negative 3x factored out. I've got the negative 6 that I've got left, and then I've got this negative 3 times the negative 7 and the negative 6x. So I have plus 21 and plus 18x. So far, so good? Okay, so I have e to the negative 3x. And then negative 6 plus 21 is 15 plus 18x. And this would be my second derivative. Again, notice, when I did my first derivative, I labeled I was about to do that. I didn't actually keep labeling, although you certainly can, but everything after that has equals, and it has what's equal to the step before. When I did my second derivative, I actually wrote second derivative then, so that it's identifiable as different than what I did before. It's no longer equal to what happened earlier. I'm doing something different. And then I've got the equals after that as well. Any questions on that one? Okay. So the title of this section said derivatives and antiderivatives, or differentiation and integration, or something like that. So that is the other part of this, is to do the antiderivative. All right, so we're taking a look at antiderivative. Basically what we're saying is that if we have a function, e to the x, just a little bit ago you learned that if you had that function and you took its derivative, it was e to the x. So what happens when you do the antiderivative? It's still e to the x. It's just, he's the best one ever. So his antiderivative is also e to the x. Of course you have plus c. But you still have e to the x. You take its derivative, you take its antiderivative, it's great, okay? So we're going to do some examples now with antiderivative for it. Okay, so first a real straightforward one. We have e to the 1 minus 3x. Clearly it's not just e to the x, okay? So what are we going to do that's going to allow us to work this problem? U substitution, you bet. So what would I let my u be? 1 minus 3x sounds good. And if we do that, then what is the derivative of 1 minus 3x? Negative 3 dx. There is not a negative 3 in my problem, so we've worked with this before, but let me remind you. What we need to have is we need to have that negative 3 on the other side. So either written like this, or you can think of it as negative 1/3 du is equal to dx. So when I'm rewriting my problem, I can put that negative 1/3 in front. I can put my integral. The e stays the same. Now what's different is that I don't have a 1 minus 3x because that's equivalent to my new variable u. And I can replace the dx with du because what I've really replaced is I've really replaced this dx with negative 1/3 du, right? All that's the piece that replaced the dx. All right. All right, so moving forward with this, I then have negative 1/3. What's the antiderivative of e to the u? E to the u plus c, yes. And then my last step would be to do what? Plug u back in with the 1 minus 3x. Okay, this piece over here is my scratch work. for my u substitution. Everything else, all those steps were equal. Okay, so far so good? Okay, let's try another one. E to the x plus e to the negative x over e to the x minus e to the negative x. This one looks really messy, doesn't it? But one of the methods that you know is u substitution. In fact, it's almost the only thing you know at this point. You've got a few other kind of tricks up your sleeve, but not many. So if you were to be inclined to do u substitution, what might you try to let u be? The bottom. Okay, so we're going to try that, and we're going to see some things happen that are handy. So if I let the denominator be u, let's find out what we get du to be. Well, the first part's easy. What's the derivative of e to the x? E to the x. Then I've got a negative, and what's the derivative of e to the negative x? What was that? Yeah, so this is e to the x plus e to the negative x, isn't it? And I need a dx on here. I think maybe somebody told me that and I didn't write it. Do you see an e to the x plus e to the negative x in your problem? Isn't that nice? It's on top. So, in fact, I don't even have any 1/3 involved or anything. This piece right here is this piece right here exactly, isn't it? That's really nice. So let's take a look at rewriting this then. So if I take this problem and I rewrite it, I've got an integral. I've got 1 over u du. What's the antiderivative of 1 over u? Natural log of absolute value of u plus c. But my u is not simply u, it is e to the x minus e to the negative x plus c. And some of you might be tempted to think, hey, maybe I can simplify something there. And you actually can't. Why not? Because there's subtraction on the inside. If I did not have subtraction on the inside, if there were multiplication or something like that, I could simplify that because natural log and e have this wonderful inverse relationship and things would be able to condense, but they're not here. Okay, last one in this section. A definite integral. So I've got the integral from 0 to square root of 2 of x e to the negative x squared over 2 dx. What do you think? All right, u substitution. When you don't have many tricks up your sleeve, you get to use the same trick a lot, don't you? Yeah. What do you think u might be? Yeah, and in fact, you kind of have to do something with that exponent because the only rule you know about e to the x is plain old e to the x, not e to the anything else. So that anything else needs to become x or you're not going to be able to apply that rule so well, right? Yeah, so this is what we have, and that's actually really nice because then what is du? You guys are struggling on this little, or nobody wants to talk to me. Negative x dx, right? The derivative of the x squared on top is 2x. That 2 will cancel with the 2 on bottom. The negative stays. This is negative x dx. So the part about this that's different than what I actually have, because I have an x dx, is the negative. Agreed? So my problem up here, which I'm going to leave the limits of integration off, will be the integral. I'll have a negative, so I'm going to put the negative on the outside of e to the u du. All right, so what's the antiderivative of e to the u? E to the u. I still have a negative because it was in front, so I have negative e to the u. I would have put a plus c here. I don't need it on this because eventually I'm going to put those limits of integration back in. In fact, before I do that, though, I need to replace the variable. So I've got negative e to the negative x squared over 2. And I want to replace it with square root of 2 and 0 using the fundamental theorem of calculus. Well, I like putting square root of 2 in actually pretty well because it's actually x squared, isn't it? So that's kind of friendly. So I've got negative e to the negative square root of 2 squared over 2 minus negative e to the negative, well, 0 over 2. Okay, so what happens when I square root a square root, I'm sorry, when I square a square root 2
Just cancel.
to become a
2.
2, which is also then divided by 2, right? Which is, okay, so I've got this first piece being negative e to the negative 1. Agreed? How about the second piece? I have minus a negative, so that's plus. What's e to the 0? It's 1. So this is plus 1 at the end, right? E to the 0 over 2 is the same as e to the 0. Usually you don't leave something written with a constant exponent, that is a numerical exponent, with a negative in there. How could I rewrite this so that it looks more traditional? The more, negative 1 over e plus 1. You might also see the back of the book combine those into the same expression. That is, you don't have a separate plus 1. If you were to combine them by getting a common denominator, it would end up looking like e minus 1 over e. Okay, because that 1 would become e over e, and then you change the order. Okay, I don't care which one you put, but either of those would be perfectly fine. Okay, any questions on that? Okay.